Okay, ladies and gentlemen, hello. Welcome back to the Design on Cloud Pavilion, which has been sponsored by Google Cloud and Microsoft. Good afternoon. I hope you've been having a great 3 days so far at DAC. We've had some great speakers up here today. We've got yet another great speaker who is coming up momentarily to talk with us about I/O profiling. Folks, I'd like for you to welcome all the way from Cambridge, Dr. Rosemary Francis of Ellexus. Let's give her a warm welcome.
Hi, thank you very much for that introduction. So today I am going to tell you how to make your workflows faster and easier to move so they can get even faster. So that is the goal of today. But first of all, I'm going to give you a bit of an introduction as to who we are. I know some of you know us already, but some of you don't. So we are the I/O profiling company. As Derek says, we're based in Cambridge, UK, the real Cambridge, and we make tools to help you understand the way you access data. So that can mean all kinds of things, anything from gathering application dependencies to running at scale to monitor application I/O running in production. And we work in a number of different industries. EDA is just one of them. We like to call it where big compute meets big data. So that's HPC, HTC, EDA, all those kind of areas. So we've got customers in life sciences, oil and gas, finance. We've recently started working with some of the cloud providers on optimizing some of their AI and machine learning workloads. And that's been a lot of fun because some of those run at epic scales. We've just done a proof of concept with AWS where we were running IO-intensive workloads that use 200,000 machines, which is really exciting. That's more than the British weather forecast. So I personally think that's extremely cool. But really, EDA is where we started out. My background is EDA, so before I founded Ellexus in order to help find problem jobs and help problem users. I'm afraid to say I was probably one of those problem users running the wrong script at the wrong time or something like that. So I understand exactly where your challenges are coming from and exactly where the challenges of the industry are. And you'll recognize the names of some of our customers on the screen there. So I'll give you a brief introduction to our tools because a lot of the examples and case studies that I'm going to be presenting today use data that we've collected from these tools. We've got two main product ranges, Breeze and Mistral. Breeze is designed to profile applications in detail. Could be a very large distributed application, but it gathers quite a lot of information, so you don't necessarily want to run that in production. Breeze will tell you what all your dependencies are. So we'll tell you about every single file, every single network location. We'll tell you where your make file is. We'll tell you which files you included. We'll tell you about that library you didn't know about. We'll tell you about the wrapper script somebody else installed for you. And this makes it super easy to migrate to the cloud, super easy to migrate from one system to another. And on top of that, we give you a lot of I/O profiling information about individual programs or individual files, so you can look in detail about what's going on. So used quite often to debug DevOps issues, kind of why does a particular program run for me and not for you, or on one machine and not for another. Those kind of differences you can pick up with Breeze, whether it's a network setting or environment setting, that sort of thing. Mistral, on the other hand, is used to profile at scale. So it's much more lightweight. It doesn't gather nearly as much information as Breeze, but it tries to pick out the important bits that you need to know in order to locate rogue jobs, understand what's going on in your system, do QA on new workflows, that sort of thing. So really, by using these two tools, you can get a very broad and a very detailed understanding of what your jobs are doing. And I'll show you how that's done shortly. So first of all, why care about I/O? So you're all sitting here, so you probably all care a little bit, but just to emphasize, a bad I/O costs you money. And in EDA, that can mean wasted compute, wasted storage bandwidth, wasted network bandwidth, or most importantly, wasted license utilization. Compute is getting faster than storage, so the performance gap is widening. A very long time ago, you could access memory twice in every clock cycle. My laptop today takes thousands and thousands of cycles to access memory if you get a cache miss. So that difference is widening. It's an even greater difference for other types of storage. And on top of that, we've now got a very complicated model of storage. There is a rainbow of solutions out there, from networked storage solutions, distributed file systems, parallel file systems, NVMe, burst buffers. It's really very, very complicated. And unless you understand your I/O, you can't make good use of those solutions. I've referenced a white paper down here that looked at cloud utilization. This company estimated that 40 to 50% of expenditure in the cloud is wasted. And for I/O-intensive applications, a huge amount of that is storage. It's very, very easy to over-provision in the cloud your storage needs, and that's where a lot of the costs can add up. So understanding your needs and making sure that you're not over-provisioning or under-provisioning is really key. So what everybody wants is to be fast, agile, and cloud-ready. By agile, I mean you need to understand your workloads, you need to be able to move your workloads, you need to be system agnostic as far as humanly possible to make sure that you can move quickly and easily and take advantage of new technologies. Cloud-ready doesn't necessarily mean running in the cloud, but the ability to run in different environments and take advantage of different settings. One of the things that's different about the cloud is that you don't decide your cloud procurement strategy and set it in stone for sort of 3 to 5 years in the way you do with in-house hardware. On the cloud, you can go clickety-click, give me twice as much memory, and suddenly you're running on a completely different system. And so being able to take advantage of that by understanding your workflows and being able to dynamically tune them is really part of that journey. And part of being fast, which is the goal. But we quite often don't have this. So it's really easy not to be fast because it's really easy to abuse resources. I'll talk about some examples of that. Optimization is hard, and it used to be that I/O was just the domain of the experts. It's too important just to be left to the experts now. Everyone wants to be agile, but it's very, very easy to get tied into a single environment or a single workflow or tool. And this can lead to very, very, very complex legacy systems that are hard to pull apart. And being cloud ready is hard when you need to dedicate time to looking at dependencies and packaging and getting your storage sized correctly and so on. So this is an example of a workflow from ARM. So this was sent to us a while ago, but it's just as relevant then as it is today. It's a really good example of low-hanging fruit in terms of optimization. This is a software build, and all of the temporary data is supposed to go to ARM scratch, to temp here, which is local storage, and it's not. It's going to ARM scratch up here. So that is harming the performance not only of the application while it's running, because Scratch is slower. It's also harming performance of all the other applications trying to use Scratch. And it's also so easy to fix you don't need to redesign the compiler or completely redo your workflow in order to change this. You just need to set the variable that tells the build where to put temporary files. You just need to change that, and the whole thing will run faster. This is another example. This is actually a workflow from a life sciences customer, but it's really relevant for you guys as well. They have very similar challenges. They don't pay so much in licensing, but they do have a lot of similar compute challenges. This is a workflow where the software in question has been really highly optimized. The I/O patterns are really super. It does use a lot of small files, but that's something that's inherent to the design of genome pipelines and part of the software that's very hard to change. The areas of software that are new, that the customer developed, are really, really super, and they've done a really great job. However, the last thing that happened before they released this publicly was that someone added a progress bar to the web interface, to the pipeline. And the progress bar knows how many small files, small output files are going to be created, and uses this to determine progress. And so every few seconds, it stats the output directory and gives the progress report accordingly. And so the number of stats that happen on the file system grows as progress continues. And by the end, we are looking at around 15,000 metadata accesses every 20 seconds. So absolutely enormous and totally unnecessary. There are better ways of doing performance, for doing a progress counter. So this is a real example of where the tools can be absolutely superb, but the deployment can just misunderstand some aspects of the IT infrastructure and make a bad decision. So again, pretty easy to fix that one. The next thing that I want to highlight is the problem with failed I/O. So this is a workflow where the tool looks for several config files, and the location of those config files is set via a variable. That variable can have multiple paths listed in the variable, and it does so. In the customer environment, it has lots and lots of different locations. The environment is a generic environment for several different workflows, and so it's got dozens and dozens of locations, only one of which has these config files. And so every time the tool runs, first of all, it checks out a license, and then you can see that here with the connect. Then it runs a whole load of failed I/O looking for those files. And this is actually just one part of the workflow. We estimated that around 5 to 10% of the runtime of this application was spent doing failed I/O. So that's not only hitting the metadata server, not only wasting compute, it's also wasting that license. And again, easy to fix, really easy to fix. So I think Meltdown and Spectre is also worth mentioning. Depending on your compute, we've got estimations from customers saying that they've seen up to a 13% slowdown. We've also got estimates from customers saying they've seen 0 slowdown. So it's something that only you can discover by measuring the impact. It's something only you can make decisions about in terms of the security impact for your system. But if you are seeing high overhead, then one of the things you can do is get rid of all that failed metadata, because every single one of those is a totally unnecessary context change, and that's where your overhead's going. So I've talked a little bit about some of the things applications can do to slow down the system and waste time. Now I'm going to talk a little bit about the sort of things that you can do from an analytics perspective in order to find these applications and really take control of what's going on. The first thing you want to do is get rid of anything that is causing huge performance issues on your system, and in order to do that you need to measure and find out what's going on. So this is a case study from a customer who had a lot of problems with the noisy neighbor problem. They're an EDA customer. Sadly, they couldn't be here today. I asked them to co-present, and they wanted to do that, but there was a diary clash, so they couldn't make it. They have a host leaf architecture where host compute nodes have got a fast network connection to the shared storage, but leaf nodes don't. Leaf nodes have got a very, very slow connection to shared storage, so their jobs are supposed to aggregate data via the host node and then write it to shared storage from there. And that works very, very well most of the time. When users accidentally write from leaf nodes to the shared storage, then the shared storage more or less grinds to a halt, and it can do that for quite some time before recovering. Occasionally, it crashes completely. And this was something that was hitting them maybe 2-3 times a week when we first got involved. They also occasionally have problems with people leaving the debug flag on and writing too much data from the host nodes. And they also had issues with people hitting metadata servers by doing too many deletes. So, in order to help them with this, we deployed Mistral. Mistral is designed to run at very large scales or even in production. You can deploy it to all of your jobs. It does this via a job starter, so it's very easy to control, very easy to turn on and off. It monitors basically anything you want it to. In this case, we set it up to monitor any shared file system I/O from the leaf nodes, excess shared file system I/O from the host nodes, and any excess metadata, in particular deletes. And in order to interpret this, the data was written out to a database and viewed with Grafana. Grafana is really cool because you can see a live view of what's going on, and you can change the viewing time frame. It'll aggregate data nicely, so you can get a kind of historical view. So you can say, okay, tell me what happened over the weekend, tell me what happened over the last month. And you can set it up to send the latest version. You can do all kinds of things like tell you, set an alert if you go 2 standard deviations away from the mean, things like that. And the idea is once you've spotted a particular issue, then you zoom in and look at the raw data. So I must apologize, there is a slight cultural misunderstanding here. I thought Jane Doe was a name for anonymous users in the United States. Turns out it's your name for anonymous bodies. So I'd just like to make it perfectly clear, the user is not dead. They have annoyed the sysadmin, but not that much. In order to maintain a good relationship going forward, they are going to fix their job and not overload the server anymore. So yeah, Jane Doe, not dead in this scenario. What you can see is this is just like a shorthand version of the information that you get. But we tell you the job, we actually tell you the host, any specific variables you want to see, like the project. We also give you the user. We tell you which program and the complete path. So if it's a script, you can see exactly which script is causing a problem. And we also tell you which file was the last one to be accessed, which is sometimes a red herring, but most of the time, if you're accessing thousands and thousands of files over and over again, then you only need to know the name of one of them to work out what's going on. And we also tell you, of course, exactly what triggered the log. So this was great. It wasn't an instant fix. But the customer, after 12 months, saw an almost complete reduction in the number of jobs overloading the storage. So a massive result there. And that was a mixture of communicating back to users, putting in place steps so that jobs that they couldn't fix or it wasn't reasonable to fix. So, for example, they were jobs needed for a particular tape out or release, and they absolutely had to run, then they could be siloed into a different system. There were all kinds of different things you can do to, and all kinds of good decisions you can make once you actually understand what's going on. So what they're moving to now is a system of quality assurance where they don't just monitor in production, they also try and proactively prevent applications from overloading the storage. So that means tracking and understanding application dependencies, making sure that everything is reading and writing to the right place, measuring I/O patterns, designing for change and trying to make sure that they are not locking themselves into particular I/O patterns, trying to abstract the I/O as much as possible so that data can be easily moved around and changed, and working on accountability. That is really not so much a technical problem as a process issue within the company, but you need to have the technical tools to back that up. So looking at accountability through feeding back information back to users about how much they're using the system, how much any particular group caused problems on the cluster and things like that, so that you can work with them to make good decisions going forward. And application dependencies were at the top of that list because it's really the best place to start. Until you've understood your application dependencies, you really have no business looking at performance. So the thing that we find with our customers, as soon as they eyeball a list of dependencies, there is something in there that shouldn't be there. For example, an area of the file system they shouldn't be hitting, a hard-coded path to someone's home directory. We see that a lot when someone has prototyped a system, turned out to be really good, handed over to someone, and then that part didn't get rewritten before it went into production in their system. Very, very easy to do, and unless you've checked it, you won't know it's in there until one day it goes wrong. So checking application dependencies, the first step in that fast, agile, cloud-ready program, and very, very simple, very, very quick. Once you've done that, then you can start looking at performance. So we give you all kinds of information about the I/O patterns per file, per program, over time, aggregate, and so on. But I really can't emphasize enough how important that list of dependencies is in understanding your workflows. It gives you the tools you need to make all kinds of decisions about how to steer your data, and gives you all kinds of information about how to move applications and make the most of new compute paradigms. So the next thing you want to do is look at performance, and actually this is really cool. This is brand new for our tool, I think released yesterday, and my developers call it the traffic light report because we look at good, bad, and medium I/O. Apologies for those of you who are colorblind. This is all clicky, and so it's very easy to see what's good and bad when you're actually interacting with the tool. Doesn't work so well on a slide. I call this the donut of bad I/O, or the donut of doom, because it really shows you how much time you're wasting in bad I/O. And we see bad I/O as all kinds of things. Small reads and writes, very bad for performance. Backwards seeks, random I/O. Those are the sorts of things that you probably, unless it's in your own infrastructure, you probably need to talk to the tool vendors about. But there are other things that you can fix yourself, like failed I/O, stats on files that aren't used, stats on files that are used. If you're spending a lot of time statting every single file before you open it, why don't you change your script to perhaps open and fail gracefully instead, and then you'll halve the amount of metadata accesses on your system. And once you've understood your dependencies and understood your I/O, then you can start to think about using cloud technologies either in the cloud or in-house. A lot of people are looking at Docker because it's very popular, but actually what we've seen amongst our customers is much better results from Singularity, which is designed not from a microservices point of view, which Docker was originally built for. Singularity is built straight away for high-performance computing or high-throughput computing workloads where you've got big, complicated applications with lots of dependencies, lots of external storage, lots of state, and Singularity handles that much better. That's not me talking, that is our customers talking. Recently did a poll at an event in the life sciences industry, and every single one of them have stopped using Docker and started switching to Singularity. And they're based in the Bay, so if you want to have a look up Scilabs. They're the guys who own the Singularity project and are going to be taking it forward and building upon the ecosystem to really turn it into a world-class technology. So now I'm going to talk to you a bit about what happens quite a lot if you don't have the right analytics. And that's often a sort of a perfect storm. I've talked about analytics from a performance point of view and an efficiency point of view, but I haven't really talked about really debugging problems and debugging the perfect storm. So I've got a couple of examples from our customers. One example is when a system was shut down over the weekend. Some keen bean came in on Monday morning and submitted a load of jobs to the cluster. They normally just get a few slots, but they got 10,000 slots all at once. And they didn't have particularly bad I.O., but all of their bad I.O. hit the file system all at once in sync. So there are lots and lots of scenarios where generally applications have got good I.O., but then there's a burst of bad I.O. So obviously, you're not going to get much performance benefit from fixing that burst because it's quite short. But what you should definitely do is put some steps in your scheduler to flag this up as an application with bursts of bad I.O. to make sure that you limit the number of applications that can be deployed all at the same time. The next example is a different kind of storm, very, very quiet storm. So this actually, 2 of our customers saw this issue. It's another EDA company, another EDA customer. One day they came in to find everything stopped. So there was, they looked at their analytics. Both companies had reasonable analytics on their hardware. They found no network activity to speak of. Nothing was hitting the file system. The job queues were getting filled up, but nothing was being dispatched. Every single slot was full, but nothing was really happening. So they profiled it with Breeze. Mistral wasn't available at that time, so they profiled it with Breeze and found that the application was hitting one license server in order to get a license and succeeding, but then trying to access a second license server that was in the environment, and that license server normally would just time out because the tool already had a license, but on this day that server had been turned off, and the network timeout was longer than the license pulse. So the entire thing just ground to a halt, just cycling on the license. So this is the sort of thing where if they had adequate metrics about license servers and things like that, then they would be able to fix that straight away, because it would be really obvious that the only thing that was going on was people hitting the license server. So in terms of monitoring and telemetry, obviously it's a balance. We've actually been contacted by a few customers and refused to do a project recently because the amount of analytics they wanted to collect far exceeded, in our opinion, the amount of data they were generating just for their actual applications, and there was no way they could handle that amount of data. So you've got to be sensible about what you collect, and there is an art to it, but you do need to monitor in order to understand what's going on, in order to feed that back to customers, in order to solve problems, in order to speed up your applications. And we believe really, so this is the kind of takeaway of the session, hardware battles will be won and lost by the availability of analytics. You cannot run systems anymore without knowing what's going on them and without measuring what's going on them. Not just now, not just in the future. You need to be able to measure what you're doing, to administer the systems you have now, but you also need to measure what you're doing for procurement. You can't decide what you're buying next if you don't know what you're using now. And in terms of analytics, I think we are really just starting to see a revolution in the way we treat analytics. It's so important to gather information now so that you can make decisions about it in the future, but we're going to be making decisions that are so far in advance of what we're doing now, which is mostly looking at a bunch of metrics and deciding which ones have gone too high or too low, in terms of using perhaps machine learning, perhaps other techniques that haven't even been invented yet in the area of analytics. I think Henry Ford said if he asked his customers what they wanted, they would ask for a better horse. And I don't know about you, but I don't ride a horse to work. I drive. And I think one day we're going to look back and wonder why we were just looking at squiggly lines on a graph. But we have to start somewhere. We have to start by doing that. We have to start collecting that now so we can make the good decisions and learn about how we need to do better in the future. So it's all about making it easy to measure, designing measurement into the system to start with, and making it easy to act on those results, not just by analyzing the data, but also putting in the processes in place so that you can get that information to the right people. So thank you very much for listening. Do we have any questions? Yes.
Very nice presentation. I'm curious, is your technology targeted at customers that are deploying in this audience EDA tools, or also can be used by the EDA providers to kind of look at their application, how much I/O they're doing, or are they doing excessive I/O that would kind of slow it down when you go on the cloud?
Yeah, so absolutely. So we've got, so Breeze and Mistral have both got different modes of use. So you can either use them in production to monitor third-party applications. You can also use it for profiling applications when you know exactly which application is causing a problem, you don't know why. You can also, we've got customers who've built the tools through the command line APIs into their build and release framework so that it's impossible to release applications with bad I/O. And a really good example of that is looking at the failed I/O slide I put up a while ago about the file system trawl. It's not exactly the same as the one I put up, but an example is where an application trawls the home directory looking for a config file. And on a clean test system, that happens very quickly. Put it in a real customer environment, and suddenly thousands of files in the home directory can cause a really big latency in starting up that application. Now you can catch that by having a zero tolerance on failed I/O, and by putting in place tests that not only look at dependencies and not only look at performance, but also look at things like failed I/O to say, okay, do we have a single failed I/O call? Let's look at that and see what it is. Okay, some of them might be fine and part of the design, but you should have a test exception that says that, so that the next time a failed I/O call appears, you can't do that. We already have got several customers using our tools to do detailed profiles whenever they update the EDA tools, because even a point release can make a massive difference in terms of the I/O profile in production. But we would like to do a lot more to help EDA vendors. So come and talk to me afterwards if you want to know more about that.